Hello everyone, in the series of learning aerodynamics, in this class let us discuss about drag equation. So in the previous classes we have seen about how to derive the drag polar equation, and the drag polar equation, if it is simplified, then final equation will be something like this: CD equal to CD naught plus KCL square, because we are just considering only the induced drag component. So we are just neglecting parasite incremental in the parasite drag and wave drag components. So by neglecting those components, and then we have a simplified drag polar equation, that is CD equal to CD naught plus KCL square. This CD naught, this CD, the drag polar equation, we are multiplying with the half rho v square s. So half rho v square s, we are multiplying this drag polar equation throughout, then that becomes CD half rho v square s equal to CD naught half rho v square s plus KCL square into half rho v square s. Then we all know that drag, when we are defining the drag component, the drag equal to CD into half rho v square. So that is what, so this equation, this term becomes drag. This term becomes a drag. So because drag equal to CD half rho v square is. Then similarly here we are just writing the that means this term alone, that means keeping the velocity square separate, and then here also we are expressing what is CL, because CL we know lift coefficient we defined L by half rho v square s. So for the steady level flight we all know lift equal to W. So this is what we consider here. So by taking lift equal to W, and then we are squaring it, then we are getting this. With this, okay, we have again this component is multiplying half rho v square, yes. Then we are squaring this component, and then we are getting k into W square, because instead of L now we are having the W, because it is in steady level flight, we have a lift equal to weight. So W square will be half rho v square s whole square. Then here another half rho v square is there. So this term and this term, one term will get cancelled. So remaining term as it is CD naught half rho s into v square. We have separated v square alone, and then here also we are separating the v square. So k W square divided by half rho s into 1 by v square. So this equal to, because we all know that these are all constant. These are all constant. CD naught half rho s is nothing but okay, that is what we are taking it as the constant. So we, if you want, we can write A equal to CD naught half rho s. Then another constant, this is also because in the given drag equation, weight and density and in the this wing area, so everything will be constant. Even this is a k we know that is 1 by pi EAR. So everything in this all those terms will be constant, so that we can take it as the another constant, that is what we represent as the B. So B equal to k W square by half rho s. So here okay, A and B we are taking it as constant. Then we are finally we are writing the drag equation D equal to AB square plus B by V square. So now we have to understand one thing. This is the parasite drag coefficient. That means drag increases. Okay, drag increases with respect to velocity. That means in square of the velocity. Okay, that is that equation we can say. Parasite drag equation we can say D equal to this drag equal to this for the parasite drag equation. So for the parasite drag is directly proportional to V square, and for the induced drag we can say it is indirectly inversely proportional to V square. So this is what, because when we are equating, then this constant will be taken into account, then that is what we are representing in the equation. So now okay, we can see these terms how it has been represented in the graphical okay, in the graph. So D equal to dy, we have drawn the graph between this vertical axis D drag and horizontal axis velocity. Now okay, as we have seen that drag is okay, increases in square of velocity, that means parasite drag increases in square of velocity. So that is what we say. So it will be like a parabola. So this curve will be like a parabola, then this curve will be induced drag curve will be is a inverted parabola, we can say. It will be a inverted line. So this is like a parabola, and this is okay, inverted parabola. Then the resultant of both only gives the total drag. So because this is nothing but total drag, we can say d is nothing but total drag. The total drag in the graph, okay, so we are getting as the this graph, this curve. So this is what the total drag representation in the graphical method. So I hope okay, this is how we are getting the drag, and how that is varying with respect to velocity, and how the drag is okay, directly proportional to velocity square for the in the case of parasite drag, and how it is inversely proportional to the v square, velocity square in the case of induced drag. What we need to understand here, okay, induced drag reduces as the velocity increases. So that is what we have to understand, because as we are going higher and higher velocity, so the induced drag effect will be minimal. So that is what. So and we are, as we go higher and higher, in that case what happen, our wave drag, suppose if we are reaching the supersonic condition, then wave drag will be coming into the pictures. So in that case our induced drag will be very very small. So that is what here we need to understand. As the velocity increases, the induced drag becoming lesser and lesser. And in the case of parasite drag, it keeps increasing. After some time, we may say that it may not keep on increasing, it may just go straight. So that is also we can understand from this graph. So I hope okay, how this drag equation plays the role okay in defining the this equation, or in defining the induced drag and parasite drag, how that they are varying with respect to velocity.